Hello and welcome. So today we are talking about sampling distributions, and this sampling part is going to be a big deal. So this is section 7.1 in your textbook. Please look on there for your practice problems and extra examples. So what is a sampling distribution? If we think about distributions, there's three types. We first start off with the population or everyone. Sometimes we call this the truth, but really the population is just everyone. It's what would happen if every single person was interviewed or every single light bulb coming off the conveyor belt was measured, anything like that. So the population is my big distribution. So think about this is everyone, but instead of taking a census or sampling everyone, we like to take samples, which then give us our sample distribution. So if I take a sample from this population, I may get this data. So it's a single sample, meaning I get different values. It's not perfect to the population because it's a sample, but it gives me a good representation of the population. So then within the sample distribution, I look at the average or the mean of each sample. And the mean of each sample is this red line. So I take sample 1, and this is my mean. I take another sample from my population, and this is my mean. I take a third sample from my population, and this is my mean. So I have 3 different sample means that I got from taking different samples. Well, a sampling distribution is taking all of my sample means and then graphing them together. So sampling is a big difference than sample. Sampling is all of the averages from each sample. So let's say I take a sample of high schoolers, and I take 50 high schoolers and get their average GPA. And then another sample of 50 high schoolers and get their average GPA. Another sample of 50 high schoolers and get their average GPA. The 3 averages make up my sampling distribution. So key point number 1, a sampling distribution is the distribution of sample means or sampling means from the sample distributions. So I take a look at the means or the averages from my different samples. So we have a couple vocab words. And we've talked about these symbols before, but now we're just putting kind of fancy notation with them. So the first one is parameter. Your parameter deals with the population. So if I want a parameter, that's the population mean and the population proportion. So the proportion we notate as P, and then mean and sigma are the mean and standard deviation for the parameter or the population. And we've seen that before. But we've also seen statistics. So my statistic comes from my sample. So statistic, sample, where parameter and population both start with P. That's how I remember, or it helps me. My sample proportion, we call this P hat. So P hat is this little P with a caret sign. We'll talk more about this next week. And then we have my mean and standard deviation for my sample. So we've seen this notation and this notation before. This is for my population and this is for my sample. The new ones are my P's, or my proportions. So important, big key point, a population needs to be at least 10 times as big as the sample taken from it. If not, we have to have a smaller sample. And we will see this rule in place, but make sure you get down this important. The population needs to be at least 10 times as big as the sample. So if the population mean is mu, proportion is P, and standard deviation is sigma, if those are unknown, meaning I don't know the population mean, I don't know the true standard deviation of the population, then I can use X bar to estimate mu, p hat to estimate proportions, and Sx to estimate sigma. So I use my sampling data to estimate my parameters or my population data. So this is all notation right now. This is just making sure we know what these symbols mean and why we use them. Let's take a look at how we actually do them in a problem. So it says identify the parameters and the statistics in each of the following settings. So we're just going to look at what we've been given in the problem and if the givens are parameters or statistics. So it says a pediatrician wants to know the 75th percentile for the distribution of heights in 10-year-old boys. So it gives me the population or who I'm getting a sample of. So she takes a sample of 50 patients. So it tells me what my sample is of. And she calculates that the 75th percentile in the sample is 56 inches. Since this is a average or the height average, this would be my sample mean. So if I think about writing out what those three pieces are, the 10-year-old boys, all 10-year-old boys is my population. So I wrote out the population. The statistic is my sample. Well, I took a sample of 50 patients. So my sample would be 50 10-year-old boys. Well, then what did I measure about them? What was I looking at? Well, it says they were looking at their height. Height would be a mean. So if I think about the notation for a sample mean, that would be x bar is 56 inches. So those are the only things I'm given in my problem. The population would be all 10-year-old boys. The sample mean or the sample height is 56 inches, and it came from a sample of 50 10-year-old boys. So that's it. That's all I have to do for this problem. Just identify the knowns or what I've been given. So let's take a look at example 2, or B. A Pew Research Center poll asks 1,102 12 to 17-year-olds in the United States if they have a cell phone. Of the respondents, 71% said yes. So if I think about my parameters and statistics again, who is my population? What did I take a sample of? So think about that. The population would be all 12 to 17-year-olds in the U.S. So the population, I just took a minute to write it, all 12 to 17-year-olds in the U.S. Well, then it took a sample of 1,102 of them. So my sample is not all of them. The sample is just the, wrong pen, the 1,102 12 to 17-year-olds living in the U.S. So my population is the all, my sample is the number that we took. Well, then it asks who has a cell phone, and of the respondents, 71% said yes. So if I think about the sample proportion who said yes, the sample proportion is my p hat, that's a statistic, and that would be 0.71. So key point number 2, we use statistics to estimate parameters. So we use the sample to estimate the population, and we use appropriate notation to define variables in context of the problem. So if I think about it, is only one sample a good representation of the population? Is taking that one sample of 1,102 12 to 17-year-olds a good representation of the entire population? Or just that one sample of 50 10-year-old boys? No, one sample is not a good representation. The law of large numbers tells us we need more samples. More samples, the more accurate the sampling distribution will be. So more samples means more accurate, and this all goes back to law of large numbers, which we talked about a long time ago. So if I take more people, or if I take more samples or bigger samples, the larger the sample size, the better the representation of the population will be. So the larger the sample size, the better representation I will get. If I think about taking a sample of 2 seniors at our high school, are they going to be a good representation of the entire senior class? Well, maybe, but maybe not. If I took a sample of 20 seniors, though, would that be a better representation? Yeah, probably. More people, larger sample size, better representation. I like to think of it like an ice cream scoop. I love Moose Tracks ice cream. Moose Tracks ice cream is my favorite. And in Moose Tracks, there's like fudge and peanut butter cups and caramel swirl and chocolate fudge and all the good stuff. But if I take a tiny scoop of Moose Tracks, I'm not going to get everything in that tiny scoop. I'm probably only going to get vanilla, or maybe a little bit of chocolate fudge with vanilla. So a tiny scoop or a small sample is not a good representation of the population. But if I take a big scoop of Moose Tracks ice cream, I'm going to get a peanut butter cup, I'm going to get some fudge, I'm going to get some vanilla, I'm going to get some caramel, I'm going to get all the good stuff. So larger sample sizes, the better representation the population will be. So in our class, we're going to have 2 words to describe our consistency and our spread. So bias talks about, are we on target? So high bias means I'm off target, but low variability means I'm really consistent. So if I'm high bias, I'm way off target, but low variability means I'm pretty consistent with my data. High bias and high variability means I'm way off target and I'm super inconsistent. I got points all over the place. Low bias means I'm close to the center, but high variability means I'm pretty spread out. But my ideal is low bias and low variability, meaning my samples are really accurate and they're really consistent. So that's a wrap. We use sampling distributions to estimate the distribution of a population, and statistics are used to estimate parameters. This is section 7.1 in your textbook, and I'll see you next time.